All right. Good morning, everybody, and welcome to your new favorite class. Yes. My name's Dr. Hart. I'll be your professor for this class. This is ME3005. I guess I can stop sharing my little lecture lobby now, so now you can see me. Welcome to ME3005. I'll be your teacher for this course. I think a lot of you have had me before, so it's nice to see some familiar faces. People that had me for 2003 last quarter, you're probably very familiar with this room. This is where I did all my lecturing last quarter. And it's where I will be hosting all the lab sections for this particular class. So before we get started, just a couple of things about how this is going to work when we're online in Teams is that during the lecturing period, while we're online here, you should be muting your microphones. And if you want to mute your camera, that's fine. If you want to show yourself on camera, that's also fine. It's nice to see that there's actually people out there. You know, I'm not just kind of like talking to the wall here. It's always nice. If you want to ask a question, you can do so by using the chat feature. So if you kind of go to the upper right of the Teams meeting chat here, there's kind of like a little dialogue bubble that you can click on. That'll bring up the chat window and you can sort of type your questions in chat. And I'll do my best to sort of respond as fast as I can to those chat messages. So sometimes I go a couple minutes without seeing it, but usually I'll get to it. All right. Last thing is I'm going to be recording these videos, the lab videos, and when I do the lectures in person, which will, take place the first one tomorrow, I'll be recording. So I ask that you please don't stop the recording. You have the ability to do that if you kind of tap on the three ellipses at the top right of your Microsoft Teams and pull out the menu, and you have the ability to stop the recording if you want. Please don't do that, so that the video kind of streams continuously and we don't have it broken up into multiple pieces by me having to restart it after you stop it. Okay, so that's that kind of the etiquette for Teams as we go forward through this quarter. All right. Now, a little bit of overview for the class. ME3005 is a little bit different than your traditional class because we have a lab component, and obviously this is the Tuesday Lab, so you're well aware of that. But how we're going to work in the lab sections is all the lab sections will take place here online in Teams. So you see I'm at my house, I'm lecturing from home, that's how they're all going to go. And what we do in the labs is going to kind of vary from week to week. Sometimes we'll just have a lecture, sometimes we'll have sort of a pre-recorded lab demonstration. So we recorded some lab videos over the summer, and you can sort of watch those on your own time, and I'll be here to answer questions about that while you do that. Or some of the lab periods are going to be reserved for taking exams. So we have 2 exams in this class that'll take place during the regularly scheduled lab periods. And so I think the first one happens in week 5, the second in week 10. So it's kind of a hodgepodge of what we're going to do from week to week, but everything will take place on Teams for the lab section. So hopefully that's clear. And I think most of you have made it here, so that's good. Okay, some other notes. I'm going to use Blackboard this quarter. I think the university generally is pushing towards Canvas, and I probably will adopt that maybe next quarter. But everything for this particular class will be on Blackboard. So materials for the labs, homeworks, exams, equation sheets, so on and so forth, available on Blackboard. You should all be able to see that, and hopefully you've gone there and sort of taken a look. I've uploaded some information for today's sort of lab lecture period, and there's a lot of information today regarding how to do technical writing correctly, and that's going to be a big portion of the lab section of this class is doing technical writing. So this is probably the first class where you've really gone in depth on technical writing. Maybe you've done some writing for lab reports in the past, but I'm going to be in your face about writing this quarter, okay? So probably at a greater depth than you've ever had before. So that's something to look forward to. Always exciting. We're not going to do any in-person labs. As I mentioned, it's all going to be kind of like pre-recorded video labs, which is unfortunate. I like to sort of get in the classroom and get in the lab and get my hands on stuff, but because that requires group work and close proximity and handing samples to each other, and you can't really do that with the current state of affairs. So it's unfortunate that that's what we have to do, but that is what we have to do. So just want to make that little note. The lectures, though, will be sort of this hybrid style. And I sent out an email kind of detailing how that's going to work, but the class is segregated into various blocks, and your block is eligible to attend the in-person lecture once per week. So whether you're at the beginning of the alphabet, you can come on Mondays. At the middle of the alphabet, you're coming on Wednesdays, and at the last bit of the alphabet, you're coming on Fridays. So that's optional. You don't have to come in person. You could attend all of the lectures virtually through Teams if you'd like. Otherwise, if you want to come in person, that's great. I would love to see you guys. It's been a while. I've been in this cave for too long now. I forget what social interaction is like, but hopefully we can work on that a little bit. Okay, so the agenda this week is we're going to talk about technical writing and why it's important and how to do it properly. And so there are a variety of things I uploaded to Blackboard, which maybe you want to follow along with as I'm going through the lecture, and I'm also going to project some slides as I sort of talk through that. But before we really get going, I just want to see if there's any kind of questions in the chat at this point. We're going to go over the syllabus tomorrow, by the way, with everybody. So can everybody hear me? Hopefully I just didn't, talk with no audio there the entire time. Let's give you a second for questions if there's any questions in the chat. Make sure you can find that chat bubble and yada yada. Okay. Well, it doesn't look like there's any questions right now. I didn't get any confirmation that people can hear me, so hopefully you can hear me. Is it okay to attend Thursday Lab in place of Tuesday? Asked Alex. Yes, you can attend Thursday. However, I would encourage you to come at your normally scheduled time. But I'm not going to, kick you to the curb if you're there on Thursday. Okay. Glad you can hear me, Kirchma. Nice to have you back. It's been a year or so. Glad to have you back in class. All right. Let's get on with it then. So today we're just going to have kind of a lecture. There's not going to be any kind of lab component. I want to do two things. I want to talk about some scientific literacy, and hopefully this is kind of like a fun lecture because I'm going to make fun of people with bad vocabulary, and that's always fun. And then we'll talk about why that scientific literacy and using the right vocabulary and not sounding like an idiot is kind of an important thing for maintaining sort of a reputation and making sure that your colleagues that you work with in the future can trust what you report and what you say. And it mostly comes down to how you communicate and the words that you use, and how if you're not communicating properly, it can sort of cause you to lose faith and trust of your colleagues. So that's one thing. And then I'll talk a little bit more in detail about specifically the technical reports that we're going to do in this class and how those are going to go, and some of the aids that I've given to you on Blackboard that will help you with writing your first couple lab reports. Okay, so on with the show. All right, I got to flip you guys over here to my writing pad. A little rusty, so taking me a hot second here, but okay. Hopefully we can all sort of see this now and see what I've projected onto the screen. So these sets of notes are available on Blackboard if you'd like to sort of follow along on your own screen, but you can probably just use the Teams meeting here to see what I'm getting after. Okay. Now, I want to talk about scientific literacy and technical writing as sort of a funny way to start this class. And sort of a way to talk about how you can sort of lose trust in your colleagues if you're not technically reporting accurately. Okay, and the first thing I want to talk about is just kind of a funny story. All right, there's this bright light, and here's this YouTube clip, or I've taken a screenshot of this YouTube clip of what appears to be this like massive UFO that's over LA, and this happened 5 years ago, November of 2015, so about 5 years ago. These people are video recording this bright light that happens to be over LA, and it's funny in the video they're talking about like this bright light, this unidentified flying object, and at one point the conversation pivots to aliens kind of landing and taking over. Okay, and these people in this video say something along the lines of, I see a bright light in the sky, it's an alien. Okay, and so where am I going with this? Well, my point is, when you talk about doing science and reporting science accurately, It's important that you don't jump to conclusions that you don't necessarily know. And this is a prime example. So you see this bright light up in the sky, like what do you know? Okay, you know that there's a light in the sky and you don't know what it is. It's an unidentified flying object, a UFO, unidentified. So how do you go from there's this bright light in the sky that I don't know what it is to it must be aliens? Like I don't really understand and see that correlation. So the Washington Post, a mysterious light that rocketed across the Southern California sky on Saturday night, sparking fears of nuclear war, an incoming meteor, and an alien invasion. These are all people jumping to conclusions about what this light is with incomplete information, was actually an unarmed missile test fire by a Navy submarine. Okay, there's a perfectly plausible explanation for what happens, but because people are so steeped in uncomfortable ideas of not knowing what it is, they sort of have to jump to some conclusion that they don't really know. Okay, and this happens all the time, right? Um, I do this a lot, and I have to catch myself when I do this, and it seems silly, but we really do this all the time. My car won't start. The battery must be dead. Okay, I've said this sentence many times living in Wisconsin. If you've lived in Wisconsin or cold places, you've probably gotten in your car, tried to turn it on, and the car just won't start. And you immediately jump to a conclusion of the battery must be dead. Okay, you don't know that. All you know is that you tried to start the car. This is an experiment that you did. You turned the key, and the result was your car didn't start. When you say the battery must be dead, you've jumped to a conclusion with incomplete information. All you know is the car didn't start. All right. You have to do further experimentation to determine that the battery is dead. Maybe you get out your, ohmmeter and you check the voltage of the battery. Okay. For instance. All right. Then if you perform that experiment and you see that, there's an overloaded voltage or something like the resistance is at infinity, then you're saying, okay, there's something going on with my battery here. The battery is the problem. I have confirmed that through experimentation. But if you just jump to this conclusion that the battery is dead, that might not necessarily be true. So you go to the, auto parts store, you get a new battery, you put the new battery in, and then you turn the key again and your car didn't start again. Well, you made a mistake in assuming that it was the battery that was the problem. And my point here is that when you're doing experimentation as a scientist, you're working in a lab, you might do an experiment where you get some information. Like, I turned my key to my car, and the result was the car did not start. All I know at that point is that the car didn't start. I don't necessarily know that it's the battery. So more experimentation is required. That's my point. So when you're writing conclusions in your papers for this particular class, you need to be very clear that the experiments that you've done or that we'll have for these lab videos definitely conclude what you're going to conclude. Okay? So we'll talk a little bit more about that with each individual experiment, but I want to make sure that you understand this idea of don't jump to a conclusion with incomplete information. There are other examples of this, something like, I don't feel well, it must have been the Chinese food. Okay, well, yeah, you don't feel well, but how do you know that it was the Chinese food? People say this all the time, like, oh, I had bad food at the restaurant the other night. Like, you don't know that. Did you, take a sample from your stomach and, determine that it was the chicken fried rice or whatever that, happened to have some higher level of E. coli than normal? Like, you don't know that. Like, don't jump to that conclusion with incomplete information, all right? You need more experimentation to have that conclusion, right? This old outfit in my closet will make me look great. Okay. Well, there's probably a reason it's in the back of your closet, right? Maybe you need a further experimentation. Maybe you should put it on and see that, oh, yeah, there's this giant hole in the side that I forgot about. Or, the sequenced vest from 1972 is not as cool as I thought it once was, right? So more experimentation is required. All right. The light in my refrigerator is out. The fridge must be dead. Okay. Well, maybe, but maybe it's just that the light bulb burned out. All right. You don't necessarily know that. More experimentation is required. Is the fridge plugged in? Is your food still cold? Like all these sorts of things. Okay. So that's my point here, is that people are uncomfortable sort of steeped in ignorance by saying that, like, this thing has happened and I need to jump to the conclusion that this must be the case. But don't do that. Okay. There's a light in the sky, it must be an alien. Like, what? How did you come up with that? Like, more experimentation is required. All right. Don't just fill in information to bridge the gap between what you know and what you don't know. All right? Be careful about that. All right? If you really don't know, you got to acknowledge that and say, all right, I need some more experiments. I need to put on that outfit. I need to, do the test on my battery for my car to see if it's actually like busted or not, right? Well, so what's the real issue? All right? Be sure you have enough information through your experimentation to know your conclusions as well as you possibly can. Okay? Other things you've probably heard in your life, and I'm kind of pivoting to a new topic, and I particularly like this. This is stolen from Neil deGrasse Tyson, the famous astrophysicist. So if you like Neil deGrasse Tyson, maybe you've heard these before, but I particularly like this. What goes up must come down. The sun is yellow, orange, red. Astronauts are weightless. The North Star is the brightest star. Days get longer. The summer shorter in the winter. At noon, the sun's overhead. Sun rises in the east, sets in the west. Solar eclipses are rare. Okay. What do all of these things generally have in common? Okay, they all have in common that they're not true. None of them is true. Okay, many of you probably have thought that at least some of these things are true. Or you've probably heard these anecdotes previously in your life, but they are not. None of them is accurate. Okay, and you have to be careful about your language and your vocabulary and speak accurately when you're deciphering some of these things. Okay, what goes up must come down. Okay, that's not true. There's an escape velocity in which you can, reach the edge of the effects of the Earth. There are many satellites that have been launched that have escaped Earth's, sphere of influence, right? So this is just not true. Okay, you've seen rockets. Anyone watch SpaceX launches? Okay, they all left and came back. All right. The sun is yellow, orange, red. Okay, that's also not true. If the sun were yellow or orange or red, or only emitted yellow or orange or red light, then you would not see any colors outside that were not yellow or orange or red. Right? The sun emits white light. That's why you're able to see colors of all of the spectrum reflected off of the things that you see. Okay. Um, Sometimes the sun appears yellow or orange or red in the horizon because it's at a particular angle and the blue lights get refracted off of the atmosphere and those sorts of things. But it's not accurate to say that the sun, emits red, orange, and yellow light only. That's just not true. Okay? Astronauts are weightless? No. There's just less gravity acting on those astronauts from the Earth than what you might experience if you were on the ground. Okay? There's still the attraction between the astronauts and the Earth. That's what's holding them in orbit, right? There's still the G m1 m2 over r squared effect that's happening with these astronauts. So this is not true. They appear weightless because all of the things around them are moving at the same relative velocities, but they are not weightless. It's not true to say that. The North Star is the brightest star. No, okay? It's the 49th brightest star. It's not even in the top 10. It's not even in the top 40, right? It's the 49th. Days get longer in the summer, shorter in the winter. All right, this one gets thrown around all the time. It's not true. All right, what's the longest day of the year? Like June 21-ish. All right. What is also June 21? It's the first day of summer. Okay. So if the first day of summer is the longest day, okay, meaning the longest amount of sunlight, is the first day of summer, that means every single day beyond that in summer must be getting less and less daylight, or quote unquote shorter, right? So aside from the fact that days don't change in their total duration, time-wise, the amount of sunlight that you get as summer progresses is actually getting less and less and less because the first day of summer is the longest light of the year, all right? Come on now. At noon, the sun is directly overhead. That's true if you're standing on the equator, but we're not. All right, if you're not between the Tropic of Cancer or Tropic of Capricorn, then the sun will never be overhead any time of the year at noon. All right, for us in the northern hemisphere, it always has a tilt slightly to the south. For people in the southern hemisphere, it always has a tilt slightly to the north. It won't be directly overhead. Okay, so that's that. Sun rises in the east, sets in the west. Again, this is an equator issue. If you're between the Tropic of Cancer and the Tropic of Capricorn, maybe the sun is rising directly in the east and setting directly in the west, but if not, that can't possibly be the case. All right? So again, not accurate to say those things. Solar eclipses are rare. This is another good one. Solar eclipses happen every couple of years, 2 to 3 years, kind of depending. And people think that that's rare, but less than okay. Do you hear rare presidential election? Like, okay, presidential elections happen every 4 years, and solar eclipses are less rare than that. So do you hear like rare presidential election coming? No, it's silly. Okay, so again, the point here is you hear all these things in passing all the time, colloquialisms, and things that people just say off the cuff with no real basis, no data, no experimentation, no conclusion. This happens all the time, not just in scientific writing, but in the media, in the world around us, especially nowadays. Things are kind of crazy. You really have to have your like antenna up for like, does this person really know what they're talking about, and is this actually true what this person is saying? I have enough information about the way that the Earth rotates and how the sun behaves and what the sunlight is emitting to know that the things that this person is saying or these colloquialisms just are not true. And so if these people are spewing colloquialisms like this and you can understand and interpret that what they're saying is just completely inaccurate, then you're less likely to believe maybe what they're going to say in the future, even if like what they say in the future might be accurate. So the point is, don't go around repeating some colloquialisms and some things that you've heard before without really thinking them through. If you don't really know them to be true, because you're going to lose faith in people, and people are going to think what you say is less accurate. Okay. Some other quotes of interest that I particularly like: math testing scores. Half the schools in the district are below average. Okay, great. That's what an average is. So for you as a newspaper reporter to somehow report half of the scores being below average as like some bad thing, you just kind of look like an idiot, right? Of course, half are below. It's what an average is, okay? So I think what this person meant to say was something like they're below some standard of reference, but that's not what they said. You got to be more clear. And so if you're reading this newspaper headline, just take that newspaper right to the trash, okay? That editor is not worth it. That person that wrote that article is not worth it, because they're reporting on math testing scores. They don't even understand what an average is. Right in the trash, right to the trash with you, okay? So like, you're immediately losing your audience if this is what you're writing. All right. This is a little bit more subtle, but has to do with control experiments. All right. 80% of airplane crash survivors studied the location of exit doors upon takeoff. Okay. This is a case of incomplete information, because you really only have one side of the story. You know one portion of the population, the portion that studied the location of the exit doors. That's one population you have information about. You need information about the population that did not study the location of the exit doors to fully make a point here. Okay? So let's say 100% of the people that did not study the exit doors survived. All right? So would you rather be in the 100% survival group or the 80% survival group? Okay? So the point is, you need the other piece of information here about the people that did not read the location of the exit doors to make a full picture of what's going on. And this is like a very, very common occurrence in scientific writing, even at the highest levels, right? People will conclude something without having a control experiment to prove their point against, okay? So this happens frequently. All right, next, this is my favorite. U.S. Congressman. I've changed my views 360 degrees on that issue. Yeah, 360 degrees, right? So everybody stand up, okay? Rotate 360 degrees. You're facing the same direction, okay? So if you've changed your views 360 degrees, you've changed your views nothing. Okay, silly, but funny. All right. Couple more funnies here, and then we'll talk about actually you getting down to this and potentially writing some lab reports in the future. I've taken some information from my own personal work. I used to work at the U.S. Army Research Laboratory before I became a professor here at MSOE. I worked on 3D printing, among other things, and composites. And recently we submitted a paper to a journal to be published with the title here, Improving Fracture Strength of Fused Filament Fabrication Parts via Thermal Annealing. Okay? Everybody that's listed here as an author has an advanced degree in engineering. Okay? At least a master's degree, 2 people here with PhDs. Right? And even in this manuscript and in this writing, there's ambiguity, and there are things that can be improved about the communication and about the writing. So my point is that it doesn't just happen at the low levels; it happens even at the upper levels, and you really have to be mindful and watch out for it. Okay, so here are some quotes from the work. All right, starting here on the right-hand side. In contrast, the annealed load displacement curve. All right, so we all know what annealing is. Hopefully, you took Schaefer's materials class or Barnicki's material class, where you're talking about annealing materials. All right, so when you organize a sentence to say something like the annealed load displacement curve, This is like I took the load displacement curve and I put it in the oven to anneal it. Okay? This is an issue with object-subject relations in a sentence. When you write the annealed load displacement curve, it's like the load displacement curve was annealed, which is obviously silly. What you mean to say is the load displacement curve of the samples that were annealed, right? You just have to be clear about your ordering of your vocabulary, your object-subject relation for the sentence, right? Continuing, none of the annealed samples failed during loading, all right? Well, this here is a little more subtle. None of the annealed samples failed during loading, so tests were stopped. All right. Again, it's sort of a control situation here. You need more additional information to make some conclusions. All right. Continuing here. The samples consisted of a chamfered base. Okay, this is like the British spelling. So PH, I don't know how that didn't get through the spell checker, so bad spelling there. With letters ARL extruded from the base at 45 degrees. All right, 45 degrees to what? If you're talking about an angle, you need to have a relative position. 45 degrees with the horizontal, 45 degrees Celsius. Like, if you're talking about an angular measurement, you need to have some reference there. Right? Also, for this particular manuscript, the title had not so great language. All right. We'll talk a little bit more about this in this class, what it means to be stiff, what it means to be strong, what it means to be tough, because those three words have very different meanings in the field of solid mechanics. But the title has poor language. You know, it's talking about strength, which is stress a material can handle before failure, and toughness, resistance to crack propagation. We want to use the word toughness because we're talking about fracture behavior. We're talking about, you know, the resistance to crack propagation. But the title itself here talks about fracture strength. So strength is a metric which is defined by how much stress a material can handle before it fails, which is not really the right vocabulary here. It's not really the right word that we want. Okay? So, last slide here. The point of all this, you're engineers. You're going to be engineers in the future. I believe in all of you. Many people think then that communication skills really aren't important. Like if you're a whiz with a calculator and you can do calculation well, then you're just going to be employed forever and everyone's going to take for gospel what you do. But that's just not really the truth, okay? You have to communicate with your peers, your bosses. You sort of have to be a salesman sometimes on whether or not your design is the best. And the most efficient way to communicate with others and get your design adopted is to make sure that you're using proper vocabulary, you're communicating the experiments that you've done properly, and all these sorts of things. And so if you communicate improperly, people are going to look at your work and people are going to look at you generally as sloppy, unreliable, inaccurate, and precise, and generally just untrustworthy. And if you start losing the trust of your colleagues and your coworkers and your boss, they're not going to give you interesting projects. They're not going to give you fun stuff to work on. They're not going to listen to you in meetings, all those sorts of things. So vocabulary is important, communication is important, and writing is important. Otherwise, you're going to end up like, you know, that reporter who talked about average math scores whose, you know, newspaper I just put right over there in the trash. Okay. So, yeah. All right. There you go. So that's the first bit of lecture for this class. And now I want to talk a little bit more specifically about this class and how we're going to work in this class going forward and what you might expect for writing in this particular class going forward. So the next set of slides here is going to be a technical writing primer, and I'm going to pull those up now. Before we go forward, any questions on my? I know it's kind of like a little bit of a silly lecture to start today, but hopefully, kind of a lighthearted way, hopefully, to sort of start the quarter. So, some jokes. You guys know I got a few jokes, not a lot. I'm not quite as good as the other Kevin Hart, but I try my best. All right. So, doesn't look like we have any questions. No one's yelling at me about my volume being too loud or too quiet or so on and so forth. So I think we're good so far. Let us continue. Now, there's a lot of writing on this slide, and generally I wouldn't advocate for a lot of, you know, text anywhere, but I'm hoping when you write your technical reports for this class, you revisit this slide, because in my mind, I want to get you guys from what I think is probably like novice or beginner writing to maybe like an intermediate level by the end of the quarter. So choosing proper vocabulary, organizing your technical reports correctly, having nice graphs, having nice figures, all these things. And this slide that I have right here is sort of how I would personally characterize individuals on their ability to write, from kind of what I think is like a novice to an expert level. And I've written a number of journal articles myself, probably over 30 at this point, and I would say that I'm still not quite at the expert sort of level. Okay, I still have work to do personally as well. So let's just talk about what I think is important, and let's talk about how you can take your writing from what is maybe considered a novice level to maybe an expert level, or at least an intermediate level by the end of this quarter. So generally, I would classify people's writing into three categories: novice, intermediate, and expert. So someone who is a novice writer, you've probably seen this before, maybe you are this classification: poor grammar and spelling, no attention paid to verb tense, we'll talk about this a little bit more, figure table captions inconsistent and irrelevant, difficult to follow and interpret methods and conclusions, no discussion regarding importance in general practice, no general structure, material presented without structural thought. All right, so that would just generally be a novice writer, someone who might say, we did this experiment, these are the numbers, and spelling errors and difficult to follow all over the place. All right. Someone who's intermediate, and where I'm hoping I might get to you guys, is the grammar is good, maybe still a little bit of passive voice. We'll talk about passive voice in just a second. Or inconsistent verb tense. Good language, but verbose. Part of being a good writer is being very succinct with your language and trying not to write 100 words when 10 words will do. Okay. Good basic structure. Some comments are misplaced. Figures and tables are well formatted, might not be useful guides for communicating overall message. And some general discussion relative to the world around you. All right. If you can get to that point, I would be happy giving you an A. Okay. Expert writing, comes with years of experience. I still have some work to do to get there. Okay. No grammatical errors, no passive voice, constant verb tense, concise, succinct language, structured formatting, no superfluous information. Everything's in the right place. Figures well formatted. All these things that you would like to see from absolute expert writing. Lots of citations, doing so properly to relevant work outside of what you're doing currently. All right, this is like PhD level and above writing and technical ability. All right, so let's talk about some of these things in a little bit more detail and what I'm going to expect from you writing your lab reports going forward in this particular class. In this class, we're going to use ASME formatting for writing lab reports, and I've uploaded the blank template for you to use on Blackboard in MS Word format. So just download that template. That'll be your base template for writing all of your stuff in this particular class. All right. I've also, why don't I just pull that in just so you guys can see it. So here's the lab report template, the ASME template that you're going to use to start each lab report. Okay, so title, authors, affiliation, you can just put student at MSOE, background material, introduction method, results, discussion, conclusions, references. Okay, so this is the template that you can use, and you'll just fill in the information from the lab as you go. Now, aside from this template, I've also uploaded my own personal template in which I've provided additional notes in sort of my own guideline. Okay, so this template with my notes about what I think is relevant and goes into each section is also available for you on Blackboard. So for instance, the abstract is meant to be a one-paragraph summary of everything that is to come. A good outline for the abstract might be as follows. All right. Introduction, discuss theory, yada yada, methods, what did you do? So take a look at all the things that I have here when you're starting your lab report, and make sure that all of the information is in the right places. You're discussing your methods in the methods section. You're discussing your results in the results section. You're talking about kind of what happened in the experiment in the discussion. Okay, so make sure all the right things in all the right places. Isn't there some musical group that has that? All the right things and all the right... Yeah. Okay. We're going to do some citations in this class, and we're going to follow the IEEE formatting. So IEEE is the most accepted for scientific writing. Every time that I submit a journal article, it's an IEEE, and it's always what's accepted. I've uploaded a document on Blackboard that outlines proper citation formats for IEEE format. Okay, so I'll bring that here. You can take a look. How to cite IEEE documentation style. right? So if you're referencing a journal article, a web article, lab report, news article, so on and so forth, this document will tell you how to do that properly. The basic idea of it is that you're going to put bracketed numbers behind anything that you're referencing. So you make some comment in your writing. The Earth is flat, okay? The Earth is not flat, but let's say that you wrote that, and you're going to cite some crazy article from the online world. Okay, fine. You can do that, but please don't do that, okay? In fact, let's do the other way around. The Earth is round. Bracket the number 2, and that reference brings you to some book or some, any science book past anyone that's 5 years old would pick up, okay? So some examples of bracketed numbers behind statements, proper referencing. If you have multiple references, you can have them in the same square bracket, separated by commas, etc. So this is how you would incorporate the reference in the text. And then at the very end, you have sort of a list of references. And this document here shows you how to properly reference a book at the end of your document. So here's like how you would reference an ebook, an online encyclopedia, a journal article, blah, blah, blah. There's lots of examples here of proper referencing for a variety of different mediums that you might reference in your writing. All right, so there's all that for Ya. Also uploaded to Blackboard. All right. Finally, Dr. Rizza has kind of written his own document that gives a lot more detail about what you might want to go through in each one of the sections. Okay, so templates here, we're going to use the same template for ME3005, talking about what your audience might be, effective communication. This is a nice document. I think there's a lot of useful information here. I think it might be a little overkill, but if you want to go through it and read it, if you have any questions about maybe what the abstract or method or discussion might look like, then take a look at that, and it should provide you enough information and gory detail to really know what to do with each one of the sections in writing your lab reports. Okay. I'll briefly discuss some of the things that are important for writing your lab reports, and when it comes time to writing them, you can sort of revisit this document. All right. Figures are usually an issue with first-time writers. How do you organize them? Do I need a caption? Where does the caption go? So figures are pictures, schematics, illustrations, and etc. Caption in numerical order and presented in the text that way. Okay, so always write figure 1 in the text should appear before figure 2 in the text. Okay, and figure 1 should appear on the paper before figure 2 appears on the paper. Seems like very logical, but I usually have to say that because sometimes that doesn't happen. All right. Label your graphs, label your axes. These are things I hope that you have been drilled into your brain since you were in high school, hopefully. All those things. Here's some examples from a journal article that I wrote. You see here that we have figure 5, and if there are multiple images in the figure, they're each separated by an Arabic numeral, so A, B, C, D, E, and F, right? Your general sort of lettering scheme. So there are multiple images in this figure, and this is one general figure. The caption's at the bottom, and the caption discusses what you're looking at. Okay, so this is tensile testing of a certain thermoplastic that I was working with at the time, and you see the progression of the tensile test occurring here. So there's a scale bar showing, what's going on here, and I'm pulling it until it breaks. And these are the load displacement curves associated with multiple samples that I had tested. All right. This is a similar looking sample, but this one was 3D printed. And so you're comparing, the as received material to a 3D printed material, and these figures are side by side, and it's very clear what's happening. You're showing low displacement, you're showing images, there's scale bars, it's easy to follow, the captions are nice. This is, hunky-dory, everybody's happy. All right. Tables. Here's an example of a good table. Tables are basically information in sort of Excel format that you want to include in your results section, let's say, and you will be making tables, a couple of tables this upcoming quarter for displaying your information. And so here's an example of what I would consider a good table. There's a title at the top, and caption goes at the top. which is a little bit weird. For tables, the caption goes at the top, and for figures, the caption goes at the bottom, so a little bit strange. And there's a heading, there's information, it's all clear, there's units, everything is nice, everything is clean. All right. When you're using or referencing tables or figures in your text, the word table and figure should be capitalized, right? So here's an example. The results of the tensile testing are depicted in capital T table 4. All right. Now equations. When you're writing an equation in your lab report, equations get their own line and should be numbered. So you see an example here, and every variable that I used in that equation is discussed in the text. So these are important things. So equations get their own line in the text and should be numbers. Here's an example. Water vapor transmission rate as a function of time, here's the variable that I described, was calculated as, here's the equation that I used. And I describe each one of the variables in that equation using English. Delta M is the mass of the system, capital A is the area of the cup opening, and T is the testing time. All right, so all the variables that are in this equation are described in the text using words for people to understand what they are. Notice that the variables here in the text are italicized so that you know that they're relating to some equation, right? So equations are useful. You're going to have to write them in your lab reports. Make sure that you're using them in this format where each equation that you give is numbered, has its own line, and you're describing the variables in each one of those equations. Okay, a couple more slides here and then we'll get you out for today. Not going to keep you the whole time. You're probably falling asleep anyway. No sleeping. Rawr, it's only day number 1. No sleeps. All right, and do we have a question? Can you have more than one equation per line? If the equations are related, you could. I would encourage you maybe to just stick with one equation per line. I know it's a little bit annoying, but that's what I would encourage. One equation per line. Okay, thanks, Jorge. Advice for writing good lab reports. Just a couple of last things here to close things out, and I want to talk about generally what I mean by things like what is passive voice and why is it bad. What are examples of information not being displayed in the proper location of your report, and so on and so forth. Okay, so first thing first, when you're writing lab reports, use past tense. Okay, if you've worked in the lab or done an experiment, you want to talk about what you did in the past. So we measured this. We dropped a 5-gallon bucket from the roof and it smashed this egg. All past tense. Okay, this is what you did very clearly. All right. The methods, result, and discussion section, that's where it's applicable. If you're talking about how your results might affect future or affecting a more global audience, like something like the results that we found here may be influential in future Okay, well, maybe you have to start using some future tense verbs there. But when you're talking about methods, results, and discussion, all should be generally past tense, okay? What did you do? What were the numbers? The results were blah. The numbers were blah. The method was blah. Past tense, past tense, past tense. All right? Need to write in non-passive language. So I want to show some examples here of what I mean by passive and non-passive language and voice. In scientific writing, you have to make claims. You have to be strong. You have to say, we did this and we found this. All right? None of this passive-aggressive nonsense, okay? So a bad example would be stress can be calculated by dividing the load by the cross-sectional area. Okay, that's very passive. It can be, but did you do it that way? You need to be clear. The stress was calculated by dividing the load by the cross-sectional area. That's very succinct, non-passive. This is how it was done. Rawr. Okay? The material may be considered isotropic. Okay, did you make that assumption? Like, be strong and valid, all right? The material was assumed to be isotropic. We assumed it. Rawr. Okay? Personal pronouns, stay away as much as you can. I, we, us, you, them, they, he, she, etc. We calculated the stress in the bar to be 100 MPa. Okay, you don't need the we. All right, the stress was 100 MPa. End. Okay, you don't need to talk about we did this, we did that. Okay, like I get it. You wrote the paper. Like you don't have to tell me we did this, we did that. Limit your use of other pronouns. All right, pronoun usage is rampant, and not only in technical writing, but also in general conversation with people. Like sometimes you're having a conversation and you're talking about 10, 15 different people, and then the person you're talking to said she did this and then he did that and then she said that, and you're like, who is she? Who is he? Like, I can't follow your story because I don't know who you're talking about, right? So limit your use of pronouns. If you say Billy did this and Erica did that and Johnny did this, like, okay, I can follow your story a lot better because you're not using pronouns all over the place. Okay, so my example here is the load on the beam was recorded with a load cell. It bent a lot when the load was applied. Okay, this pronoun it, what does it refer to? Did the load cell bend a lot? Did the beam bend a lot? Did the load bend a lot? All three of those things are nouns in your previous sentence. And so when you're talking about it bent a lot, when you're talking about it, what does that refer to? You have to be clear about it. All right? Say something like, when loaded, the beam deflected laterally. All right, now I understand. You're using a proper noun. You're not, well, it's not a proper noun. You're using a noun, not a pronoun, to describe very specifically what happened. Right? Be succinct. All right, I see this a lot with novice writing, is that people use a zillion words when you could just write like one sentence. Okay, so here's an example. The yield stress is a region on the stress and strain curve where it starts to flatten out or slowly rise after previously being purely linear, which is a linear elastic portion of the curve. Some materials have a yield stress and some don't, but in this lab, the samples did have a yield stress. You can calculate the yield stress as a stress, which is a stress to, oh my gosh, I'm tired, okay? You could clean all that up by just minimizing your vocabulary, minimizing your words in a very succinct statement. Though not present in every material, the yield stress is calculated as the stress at which the linear elastic character of the solid material is lost under incremental loading. Oh my gosh, like a breath of fresh air. I feel better. I feel lighter. I lost 5 pounds. Okay, that's how I feel after reading that. Obviously, follow other well-established writing practices. Don't end sentences and phrases with prepositions. I say this all the time. I guarantee you guys will do it. We loaded the sample up. All right, up is a preposition. It doesn't belong at the end of a phrase or the end of a sentence. We loaded it up, y'all. Okay, no. The sample was loaded. Period. That's it. That's all you got to say. Adverbs. Fresh squeezed lemonade. God, that one drives me crazy. Every single time I see like an advertisement for like lemonade. Fresh squeezed lemonade. Oh, fresh is not an adverb. When you're describing how it was squeezed, you need an adverb. All right? Freshly squeezed. How was it squeezed? It was squeezed freshly. Sounds a little silly, but it's the correct way to say it. All right? I'm going to eat healthy. Oh, you are not going to eat healthy. You're going to eat healthily. All right? Use an adverb. The beam bent up. Oh, the beam bent vertically. Much better. All right. Continuing with location of material. A lot of times students will, or just people in general, will put information in the wrong location of a report, even though that information is useful and has validity in what they've written. So let's take this phrase here. The yield stress was calculated using the 0.2% offset yield method. The yield stress was 30 MPa. This is outside of the normal yield stress value expected for high density polyethylene. Awesome. I mean, what you have written there is fantastic if you're writing that in the conclusion section. However, if you're just specifically writing in, let's say, the results section, then there is a lot of information that is misplaced here. Okay? The yield stress was calculated using the 0.2% offset yield method. That is a method. Okay? That sentence belongs in the method section. You're describing how you calculated something, the method you used to calculate, that belongs in the method section. All right? The next sentence here, the yield stress was 30 MPa. That's a result. That belongs in the results section. So if you're writing in the results section, perfectly legit to have that sentence in there. Otherwise, it doesn't belong anywhere else. Right? This is outside of the normal yield stress value for high density polyethylene. A perfectly valid statement, but that belongs in the discussion, right? Because it is not a result. It is not a method. You're discussing the result in its relative nature to other pieces of information that you might know. Okay, so you have to be very clear about the information that you're providing and what section it goes into. All right, last slide. Couple of final things. Wording and vocabulary, and we talked about this with sort of that first deck that I brought up about being clear and not looking like an idiot because you need to use the right vocabulary. We measured the stress. seems like a legit statement, but it's actually very difficult to measure stress directly. Usually what you're going to do is you're going to put a strain gauge onto a piece and then measure the changes in the resistance of the strain gauge and then use, let's say, Hooke's law to relate strain measurements that you have to stress values. Okay, so it's pretty much impossible to measure stress directly with an instrument. Okay, what you want to do is changes in the resistance of the calibrated strain gauge, which you might have put on your piece, was used to determine the strain at discrete locations of the structure. Okay, that's completely legit. Changes in resistance you can measure with an ohm meter. All right, that's something that you can measure. From strain measurements, we use 1D Hooke's law to calculate the axial stress. Excellent. Okay, you measured changes in resistance, and then you used Hooke's law to calculate the stress. You did not measure the stress directly. Okay, be careful. The elastic modulus of the epoxy was 2 GPa, stronger than most polymers. Again, this is a vocabulary issue. When you're talking about the elastic modulus, that is the stiffness. Okay, modulus is stiffness. Strength and stiffness are not the same thing. All right, strength is the amount of stress it can take before it breaks. Stiffness is the amount of deformation that you have in the material under a certain amount of stress. Okay, different things. So be careful about vocabulary. Figure 4 illustrates the design concept. Again, this is an object-subject issue. Figure 4 can't illustrate anything. It's a figure on a paper. It doesn't have a pencil in its hand writing stuff down. Okay, it can't illustrate anything. All right. What you mean is the design concept is illustrated in Figure 4. Figure 4 is the object of the sentence, right? It's not the subject of the sentence. The design concept is the subject, and that is what is illustrated in the figure, which is the object. All right. So again, be clear. All right. A lot of rambling today, a lot of talking. I know. The periods going forward will be a little bit more interactive. I know I did a lot of talking today, but hopefully you found it at least somewhat entertaining. That's all I have for you today. Reminder about lecture tomorrow that the B block meets tomorrow. So if your last name is in the middle of the alphabet, you can come to L100 for lecture tomorrow. Otherwise, we'll be seeing you virtually through this medium. So if there's no other questions, thanks for coming today, guys. I know it's a strange time, a weird situation that we're in. I don't love it. I know you don't love it. Well, maybe some of you do love it because you're probably like in your, pajamas right now or something. I don't know. But I wish we were in person. I wish we could do these things for real. Unfortunately, we got to do with what we can do. So thanks for coming. Hopefully we'll see some of you in person tomorrow. Otherwise, the rest of you online. And I hope you have a good